Hi, today I will introduce you to parametric equations. In Calc BC, we're introduced to two more systems to help us graph equations. So far, we know how to graph Cartesian equations, and parametric equations are good for graphing equations that fail the vertical line test. Here's an example of a simple problem. As you can see here, the x and y equations of the particle are functions of time and have separate equations. These two equations are useful for describing a curve and are given a third variable, t, which determines the point xy. Therefore, when you solve the t in the x equation, you get tx, and when you solve out the y equation, you get ty, showing that each value of t gives a point on the curve, xy. As a result, we can also plot these points on a graph, determined by several values on the curve, so we join them together to produce a curve. This represents a particle moving along the curve in the direction of arrow as t increases. As you can see here, x can be any real number from negative infinity to positive infinity, and y is bounded on top by 21/4. We can also eliminate the parameter t by converting one of the equations to a t equation and substituting it into the other equation. This curve is a representation of y equals negative x power 2 plus 5x minus 1. Now that you know the basics of what to do, let's apply this to a harder problem. X and y described another path of a particle. First, let's eliminate the parameter t from this set of equations. Recognize that x divided by 2 equals e to the t. This was gotten from the x equation. Next, you can see that this is the equivalent of et to the power of 3. So therefore, you can now plug this into the y equation. This would now be y equals cos 1 plus x over 2 to the power of 3. This is a representation of the function with respect to y and x. This equation is also limited from 0 to 3/4. Therefore, as a result, x is bounded by 2e 3/4 and 2 equals 0 from where we plugged 0 and 3/4 in. You may think that from y, we might need to do a little bit more work to get the correct range of y, but it won't be as much extra work as you think. We know from the behavior of cos that the range would be bounded from -1 to +1, so that's exactly what our bound is. From here, I can quickly locate the coordinates. After figuring out these 7 points, we can quickly plot this on the graph. So at t equals 0, 2 comma cos of 2 is here, and then the rest of the plots go in the same way. This is representative of this function. Lastly, let's try out an equation with trig. At first, it might be hard to see how to remove the parameter from this parametric equation. However, keep in mind of this identity. You know that x over 3 equals sine 1/3t, and then y over -4 equals cos 1/3 t. To format this like the identity, this is equivalent to keep in mind that the identity holds as long as the argument of both functions 1/3 t is given to this format. Therefore, this parametric curve is a representation of an ellipse. Now, you don't need the individual xt plots and the yt plots. Instead, you can just use this formula to find the ellipse. While graphing parametric equations, I don't believe that many mistakes can be made while graphing the x and y coordinates. Converting to a Cartesian equation is very simple, where you change one of the functions to be equivalent to t and substitute it into the other equation. The biggest trouble that you can possibly have is in recognizing and using the trig identity, sine x squared plus cos x squared equals 1, where you have a sine and a cos with the same argument. In this case, the argument was t over 3. Otherwise, I think that parametric equations are just as direct and simple as graphing y functions. To help gain proficiency on these type of problems, I also created a worksheet of 19 problems for you to get more familiar with parametric equations. Thanks so much for watching.